What's up, everybody? Today we're putting on our nerd glasses. Ow. And talking about why your cool 3D prints break, like this one did. More after that intro. Kinda looks like an egg. What's up, everybody? Welcome back to Make It and Break It. My name's Andrew, and I'm taking these goggles off because they smell like onions. Today, we're talking about the anisotropic mechanical properties of FDM 3D printed objects. Hold on, don't turn away. I know when I say things like anisotropic mechanical properties that a lot of people, their minds just start going off somewhere else. And to be fair, if you didn't go to school and spend a lot of years learning about Young's modulus and Poisson's ratios and all that sort of stuff that comes with, you know, engineering degrees, that really nobody really cares what any of that stuff means. But we're going to break it down really simply for you, give you a couple of examples, and show you just how strong some of this stuff can be when you design it and build it in the correct way. Anisotropic, what does that mean? Well, essentially it means the material properties change depending upon the direction they're measured in, or the direction on which the force is applied. In simple terms, something that's a uniform size will break differently at different stresses based on the direction in which you stress it. The simple thing, wood. Wood is anisotropic, so we're going to use this in a demonstration in a little bit. But those of you who work with wood a bunch know that wood is stronger when you're... Phone call, hold on. Did you just video call me? Hello?
I butt dialed you, I guess.
Oh. Dad butt dialed me. Technology, right? Anyway, I was saying, wood is anisotropic. Those of you who worked with wood know that wood with the grain is stronger than wood against the grain. And you see that in like the major leagues on like wooden baseball bats. You actually specifically line up the bat so that when you hit the ball you're hitting with the grain so you don't crack the bat. Whereas if you get in and hit it against the grain, the bats will crack a lot easier. In the automotive world, carbon fiber is anisotropic. It's very strong when you pull in tension on the little carbon fiber strands, but it's very weak if you're bending the thin versions of those strands such that you're not actually pulling on them, or if you try and compress it. So, anisotropic. Its strength varies depending on the direction of the load. 3D printed materials have the same thing, and it really comes from the way they're made. So when you're making stuff with a 3D printer, what you're actually doing is you're taking strands of material, this sort of stuff, right? This is plastic that's in a strand version. Running it through a hot glue gun, hot glue gun, and putting it down on a flat piece of glass or aluminum or something like that, one layer at a time. So to demonstrate that and show why it's what's going on here, we're going to use some pieces of wood. So a 3D printer puts down one layer of plastic, a second layer of plastic, third layer of plastic, and so on until you build your part that can be super complex, like something like this. Right? This is a light holder and instrument cluster holder and everything for a motorcycle. Or very simple, like this little test bracket, which we'll talk about in a little bit. If you recall back to the time when we were testing some materials, what happens here is that when you build something like this, when you build it layer by layer by layer, you create weak points between the layers. This interlayer boundary is the weak point in most 3D prints, and pretty much every 3D print that fails because a layer separates from the one next to it like that. That's typically because either you're putting a bending moment on it, you're bending it so that they want to split apart, that'll happen, or if you are pulling these apart, so you set it up somehow so that these layers will want to pull apart when you load it up and stress it. That's typically where they'll fail. In our testing right over here on this corner here, we would load these things in different ways, and it would always fail when this layer separated from another layer, like that. And that's what happened here. So if you get in here close, semi-close anyway, you can see this ear separated from the rest of the piece. It's broken in somewhere. This is what it's supposed to look like. You can see this side, yeah. And this side broke off. And it broke off because this clearance was a little too small, and so it forced things apart. And when it forced things apart, this layer separated from the layer above it, like this, and cracked it open. Now this piece here is something that's pretty close to something I would consider for a final product on our Project Hyper 10 array for holding our lights and instrument cluster up on front. But it can't be the final product because it's missing a key feature, which kind of is what prompted this video. And it's missing a way right now to attach a front fairing, something that'll cover up all this, and when you put all this wiring in here, it kind of covers it from the front and from the back and keeps everything looking tight. There's a lot of ways to do that. You can just bolt through holes, kind of like what's going on here, but I was exploring Rif Nuts. So Rif Nuts are a way. It's a rivet. If you've never seen a rivet, let's get in close here. It is a rivet that is also threaded. So it essentially creates a threaded insert for you to go in and, you know, repeatedly install and remove pieces. And it makes things real easy so that you can just bolt stuff, you can just screw stuff in, like a front fairing, without having to go access the backside. Makes service a lot easier, actually simplifies a lot of things. So I was coming up with the design for that front instrument cluster mount that incorporated these little threaded inserts, and I created these brackets similar to this one, not this specific one, to test out if or what orientation I needed to print the material in order for it to survive the riveting process. So what I did is I designed this bracket, and maybe I'll get this bracket here, and I printed it in this orientation. So if my hand is the build plate, I printed it with one side down and one side coming up, because that tests both cases. That tests us installing a Rif nut in this direction. So the Rif nut, when you install it, it actually compresses on both sides of it. So it tests us compressing it like this and installing it through this. And the thought was that if you install the Rif nut this way, when it compresses, it's going to compress and probably split these layers. Whereas if you install it this way, where it's going through these layers, and you compress these things, you can see these are not going to really split in that way. So the idea was that we're validating the assumption that our build orientation will change how successful we are at installing a Rif nut here. And we were very successful, actually too successful, and I'll show you that in a minute. So this is what it looks like. Let's take a look at that. So this is what a Rif nut looks like installed on some polycarbonate. So these are made out of polycarbonate. That's kind of the material I was looking at making this front instrument cluster out of, because it's very tough. That's why they make bulletproof glass out of it. You can see how these things installed, and this thing was printed in a different orientation. This thing was printed so that all the layer lines, it was printed in this, instead of this orientation, it was printed in this orientation. So this tested the weak points twice and ended up being a really cool cross section. You can see it's split along in between a layer. This one was printed in the orientation I discussed earlier, with this side with the currently intact Rif nut installed, printed down, and this side printed up. And you can see this one cracked, right? But this one didn't. In fact, this installation is so strong, I actually broke the Rif Nut tool. That's right. If we take this out, it's still threaded in here. This right here is the threaded insert that is used to compress these Rif Nuts in place. I broke that on this piece. So you can see that the orientation made huge differences on the toughness and strength of the part in this orientation, and we've tested this other ways, but I wanted to make this specific video to kind of highlight the sometimes significant differences in strength that you'll see between the two parts. So I think that's about it. This is just a quick tips video, lessons learned video, stuff I pick up as I'm going through some of these projects we're doing to help you guys get the most out of your 3D printing. And just keep in mind that if you're trying to print end-use parts, your orientation of your print is very key. Because if you want to print something that'll snap, which might be useful, you'll want to print it so that they snap. And if you want to print something that will break your steel installation tools, print that in a slightly different orientation and you'll get it done. So thanks for watching, guys. My name's Andrew. This is another Make and Break It YouTube video. Like, comment, subscribe, do all the YouTube things, click that bell icon, and check out the rest of our videos where we got more motorsports content, fabrication content, and some stuff to help you bring new fabrication techniques into your own home garage. So thanks for watching, and I'll catch you later. It doesn't look too bad, right?